Every piece of physical infrastructure begins with a mathematical abstraction. Surveying is the foundational science of determining the exact three-dimensional position of natural and man-made features. But civil engineers face an immediate problem. The physical surface of the Earth, known as the geoid, which is based on gravity and mean sea level, is incredibly irregular. Its lumpy geometry makes direct mathematical computation impossible. To build anything, that chaotic physical data has to be translated into a smooth, computable shape called a reference ellipsoid. For smaller, localized projects, surveyors project this data orthogonally onto a flat plane, resting tangentially against the ellipsoid, allowing engineers to work with standard plane geometry. However, this flat Earth assumption has a strict physical limit. Once a project extends beyond 10 to 15 kilometers in any direction, the curvature of the Earth creates a massive mathematical gap between the flat plane and the ellipsoid. Bridging that gap and converting raw planetary geometry into usable construction data requires highly specialized domains of practice. Without this precise mathematical translation and a computed coordinate datum, safe infrastructure design is literally impossible. To manage the vast scale of physical variables, spatial data collection is divided into 4 primary branches. The first is engineering surveying. During a project's design stage, engineering surveyors capture large-scale topographical data. This forms the basis for digital ground models, or DGMs, ensuring the architect's plans actually fit the existing terrain. Once construction begins, this branch pivots to setting out. This is the process of taking those abstract digital coordinates and establishing physical marks on site, guiding the exact placement of structural elements. Even after completion, surveyors remain involved. For massive retaining structures like dams or bridges, they monitor long-term deformation to ensure ongoing stability. The second branch is cadastral surveying, which is strictly concerned with the establishment and management of legal land boundaries. A structure built across a boundary line requires either purchasing the adjacent land at a premium or tearing down the work. Cadastral precision prevents these multi-million-dollar encroachments and territorial disputes. The third branch, hydrographic surveying, extends this control into marine and underwater environments. Historically, this involved mapping coastlines, defining mean high water indicators, and locating seabed hazards to produce safe navigational charts. Today, hydrographic spatial data is vital for positioning offshore oil rigs and routing underwater pipelines in extreme open water conditions. The final branch is utility surveying, which maps the complex web of infrastructure hidden beneath the surface. Surveyors use non-invasive tools like ground-penetrating radar to detect telecommunication cables, gas mains, and water lines without digging. By charting these buried assets, construction crews can excavate safely, avoiding accidental strikes that cause massive outages or physical harm. Together, these 4 disciplines form a comprehensive spatial shield. They guarantee that a project is structurally sound, legally compliant, and environmentally viable before any ground is broken. As infrastructure projects scale up, they inevitably cross that 15-kilometer threshold. At this scale, teams must employ geodetic surveying, which mathematically factors in the Earth's curvature. Historically, achieving this relied on optical instruments. These required clear lines of sight between control points, limiting the speed and range of data collection. The solution to the line of sight problem came from aerospace. Early artificial satellites provided the first global geocentric tracking systems. This evolved into modern Global Navigation Satellite Systems, or GNSS. These receivers compute positions within a global, three-dimensional Cartesian coordinate system, like WGS-84. GNSS technology now enables real-time kinematic positioning. This allows a surveyor to capture centimeter-level accurate coordinates continuously while moving across a site. At the same time, airborne remote sensing and UAVs have replaced tedious single-point measurements with massive, rapid aerial data capture. For intricate physical environments, terrestrial laser scanning uses LiDAR pulses to generate highly accurate 3D point clouds, capturing millions of geometric coordinates in seconds. Managing this sheer volume of information requires a central digital hub, which is the role of Geographic Information Systems, or GIS. GIS takes disparate datasets, the cadastral boundaries, utility depths, and topographical elevations, and organizes them into specific analytical layers. The discipline has shifted from measuring individual points on the ground to managing continuous, massive digital environments. Because of this technological shift, the modern surveyor's identity has evolved. They operate as comprehensive geospatial data managers, processing and synthesizing vast information. The integration of GNSS hardware, laser scanning, and GIS software unifies the engineering, cadastral, hydrographic, and utility branches into a single, reliable framework. This framework is the only mechanism that ensures abstract architectural designs are actually compatible with the physical reality of the Earth. Absolute precision within the digital ground model is the ultimate guarantor of safety, legality, and viability in the built environment.